All right, so here's the deal. The paper in front of you, the one you got off my desk, we're going to be talking today about moving three-dimensional objects in space and relating them to two-dimensional drawings on your paper. Your paper's got both things demonstrated on there. The inner set of circles, so you see your Earth circle in the center. The inner set of circles is going to be our view from above looking down. So we're going to pretend we're out maybe standing on Polaris, the star system, looking back at Earth from above. So we're going to see the North Pole up here. And what we're going to do on the computer here is we're going to be able to see, get it. We're going to be able to use my phone.
Whoa, oh my god.
That's really black.
Your phone really said Android quality.
Yeah, it is Android quality.
It's iPhone though.
It sounded nice. Just
Okay, we're going to be able to look at this system from above. So the first thing I want to do, we've got the sun coming from here. I'm going to move the moon for a second. We're going to focus on the Earth for a moment.
wow.
Okay? Now the sunlight's kind of throwing us off coming through the window, but we'll do the best we can with it. So Earth, alright, if you notice, Earth is a sphere. Spheres illuminated by one light source are always going to be halfway illuminated and halfway dark. And that's what you can see on Earth right now. The side nearest the sun is experiencing daytime. The side furthest from the sun is experiencing nighttime. Pretty simple?
Mm-hmm.
Alright? So, as Earth rotates throughout the night, or throughout the day, folks are going to move into that light side and back into the dark, into the light, into the dark, so on and so forth. And that's what's going to cause our daily day and night cycles. Good so far?
Yeah.
Okay? So what I want to do first, on your Earth, go ahead and let's draw what we see. Sun coming from this direction, which means this part of the Earth closest to the sun is going to be illuminated. So draw yourself a line down the center of your Earth. Leave the side that's in the daylight white. So the general rule is if it's light, leave it white, and then we're going to shade the shadow. So shade the opposite side. No? Yeah, I can't take a movie right now. Sorry. Alright, bye. Alright, so again, any sphere in space is going to be halfway illuminated. So as we're working through this, try to remember we're looking at a three-dimensional system and we're trying to draw it in 2 dimensions. Okay? The next thing we're going to do, we're going to look at location A. So I've got this system back here set up to mimic what you've got on your paper. So we've got sun coming from the direction where my marker is. So we've got that light representing the sun. We've got our moon. We've got our Earth. Right now it's in position A, correct? Should be labeled on your sheet there as A. From above at location A, go ahead and draw what you see on the board. Ignore the toothpick sticking out of it there. Draw the Earth as you see, the moon, as you see it from above. Shade it the way you should see it. And guess what? It's going to look exactly like the Earth we just did was. So you're going, folks, hey, just listen. Go to location A on your paper. The inner circle is the above view. So this is, we're looking at it from above. And hopefully you can see that half of it is illuminated over here, and half of it is in shadow over here. So go ahead and color this in the same way that we did our Earth. Half of it is illuminated, half of it is shadowed. Does that make sense? It's a sphere in space, so it's going to be halfway illuminated, halfway in shadow. Okay? We'll get there in a minute.
Okay.
The next thing we're going to do, move this out a little bit, and we're going to actually put ourselves in Earth's view. So I'm going to put my phone down here, We're going to look out at the moon. We're going to move back a little bit. There we go. Okay? All right, so this is daytime. In our model, we're experiencing daytime. And you know it's daytime because we got the sun shining on us. Okay, we're looking out from Earth. We see the sun. If we can see the sun, it must be daytime. Also in the daytime sky, I see the moon. There's the moon. What do you see on the moon? How much light is being reflected back at you? None of it. 0 of the sun's light is being reflected back at us right now. Okay, now you might see a little edge of the light kind of bending around right there. Ignore that for now. Okay, so during the daytime here, if I was standing on Earth, looking out at this moon, I'm only going to be able to see the shadowy part that's facing me. I won't be able to see any of the illuminated side because it's away from me right now. Does that make sense?
Yeah.
All right. So go ahead and shade your from Earth view in the way you're seeing it on the screen, which means it should look exactly like your first page of your flip book did, which should be totally shadowed. And before I forget, did anybody not give me their stations paper from last week, other than the folks that were absent Friday? Anybody who was not absent didn't give me their station paper, please make sure I get that. And then Samara, do you have your flip book?
Yeah.
And Kate's flip book. Love it. I'll get the stapler here in a little bit. And mine at the end. Jessica flip book. Love it. Ariana flip book. Make sure I see it. Simon flip book. Love it, love it, love it. Avery flip book. See it, I see it. Ava and Ava flip book and flip book. Love it. And Marley flip book. Love it. And Laura, did you get yours done?
Yes.
You did, okay. And Haley flip book, I think I saw yours actually. Wyatt, I saw his. Dominic flip book. Love it. Fantastic. All right. So let's carry on with our moons. Now, this moon has a special name. You've already labeled it. Hey folks, we're turning over a new leaf here in February. I'm over here. We're looking at this moon. That's what you're doing. Okay? We're going to label this new moon. It's the same one you have on page 1 of your flip book. Yes, sir. That's because I already checked yours off. I was just making sure I had everybody. I had checked yours off when I stapled it, I believe. So this is a new moon, and this is what we use as our reference point for the beginning of the moon phase cycle. We call it a new moon. Every time it gets back, after its revolution, it gets back to the new moon. It's another new moon, and a new cycle of phases starts over. The whole process takes approximately a month. We're going to give some more specific numbers a little bit later. But for now, it takes about a month to do one of these cycles of phases.
Doesn't it take 20 seconds?
We're going to get there in a little bit. Okay? So, that is our new moon. We're now going to move the moon to the next spot, location B. Kind of in there. All right? Agreed? Location B?
Yes.
And we're going to do an overhead view down on it. So go ahead and shade what you see. Leave the light white. Shade the shadow. And kind of what Dylan had already said, it should look the same. Because we have not changed our relationship with the sun and our perspective from overhead. That's the same. Nothing has changed about that. So when you go to draw this, it should look exactly the way you drew it in location A from above. So we're working on the inner set of circles right now. Now, Dylan just said it, I just referenced it. it does not matter where I move this moon, as long as I'm looking at it from this overhead perspective and the sun is on my right-hand side, like it is on your diagram, no matter where this moon goes, it's always going to look halfway illuminated and halfway dark. If I put it over here, halfway illuminated, halfway shadowed. If I put it over here, halfway illuminated, halfway shadowed. So what I want you to do, while we're there, I want you to go to all of your inner circles and shade them the same way. Now, here's the really important thing to remember while you're doing this, and for the rest of the period here while we're drawing on this. Keep your paper oriented the correct way the whole time. Can I borrow your paper, please, Caleb? In other words, make sure you can always read the writing correctly like this. Don't tip your page, don't turn it upside down, because you're going to end up shading on the wrong
Is that
sides.
sideways? A little bit crooked right here?
That's okay, as long as if it's just a little bit, that's okay. So all of your moons should look identical to what you've already drawn, going around the entire inner circle at this point. So go ahead and cut them all vertically like this in half. Shade your left-hand shadow, because the right-hand side is your sun. And you can shade them a little neater than I am. And that way we won't have to keep going to that top-down view. We can just worry about the Earth view.
Are we on FaceTime with that other
Yeah,
camera?
Google Hangouts, yep. All right, so I'm going to put this back where we were, location B. And when you're done shading all your inside locations, you can go back to location B, go to the view from Earth circle, and you can shade what you see on the board right now. This should look similar to pages 2, 3, 4, 5, 6, and I think maybe 7 as well. It should look similar to what you have in your flip book already. So if you can't quite understand what's on the board there, you can look at your flip book for reference. So we're working in box B, circle B. So the light's coming from the right-hand side, from Earth's perspective. So we're going to draw a little shape there on the right like that, and the rest is going to be in shadow. Now we name these moons based on two things, based on whether they're gaining or losing light from the last phase, and by the shape of the light. So, from our first phase A to our second phase B, did we gain light or did we lose light? Well, we had to have gained light. There was no light reflecting here. Now we do have some light reflecting. So this is a term called waxing, which you should be familiar with from your stations last week and your flip book. The second part of the name is going to be based on the shape the light makes, and if you've ever been to a Thanksgiving dinner, you've probably had crescent rolls. You know, you take the Pillsbury can, you snap it open, you roll the little things up in the triangle shape, and they end up coming out in that crescent shape. C-R-E-S-C-E-N-T. Please spell it correctly. It's right in front of you. And if you can't read that, it should be in your flip book already. Okay, so that moon is called a waxing crescent. Yes, ma'am.
Why is it called a waxing crescent?
Waxing refers to gaining light. Crescent refers to the shape. Christian?
Are there like a bunch of different forms of like the word waxing?
What do you mean forms?
Like, there's like getting,
Oh, different meanings for it?
yeah.
Yes,
So
absolutely.
like, Does it all have to do with like basically the same thing? Because there's like waxing, like something to do with like a candle, and there's like chest hair
Well, that's,
waxing.
yeah, that's referring to the actual substance wax, which is different than this.
Very well.
All right, now, like your flip book, if you watch here, that's a waxing crescent. See the very, very little bit of light that's on the right-hand side there, just a teeny tiny little crescent shape?
Yeah.
As the moon revolves throughout the month, we get more and more light on that. It's still called a waxing crescent. It's just more illuminated than it was earlier. Just like your flip book has, I think, 6 different waxing crescents drawn. It's the same idea. It takes time to go from this new moon to our next main phase, where we're going to put it here. And it's kind of hard to see. We got some reflections going on around here. Do the best you can. It should be about halfway illuminated. The light's still on the right. And I believe this is page 8 in your flip book, if you want to look at it. Yeah.
You said that the light's still on the right.
The light is still on the right. So I left the right
Oh, okay,
white
yeah.
and shaded the shadow.
Oh, I.
I'll try to do the other period. Now, did we gain light or lose light from B to C? We gained. So we're going to call this waxing again. And this one has a special name. We don't name this one based on the shape of the light. We're actually naming it based on something different. Do you remember?
Is it gibbous?
It's not gibbous yet.
First quarter?
It's a quarter.
Oh.
It's a quarter. Now, excuse me, we're not naming it based on the shape of the light at this point. We're naming it based on where it is in its orbit. The orbit takes about a month to go from our start A to our C quarter phase. Takes about 1/4 or a quarter of a month, about a week. Okay, so think of it like a basketball game or a football game. You start here, beginning of the game, it's a new game. Halfway through is halftime, right? But between halftime, you stop at the end of the quarter. So this is the end of the quarter, another quarter, another quarter, another quarter. 4 quarters. This is the end of the first of those quarters. So we could call it waxing quarter, or like we named it in your booklet, you could call it a first quarter. They mean the same thing. Okay, so whether it's a waxing quarter or whether it's a first quarter, it's this moon they're referring to up here. It has finished 1/4 of its revolution around the Earth at this point. Christian.
So like a quarter of a month is a week.
Approximately, yeah.
And-
Dylan?
So, wouldn't wouldn't the moon be spinning too? So wouldn't you see like different sides of it
We'll talk about that in a little bit.
throughout?
Jessica?
Why is that there?
Because I'm recording the board. Okay, if you guys have questions from now, write them down in the back of the paper and I'll try to get to them at the end of the period. I gotta get moving here. All right? As we move now, watch the board. Here it goes. That quarter is going to start getting more and more light. More and more light. We'll stop it about here. Go ahead and draw what you see. Whoops.
You dropped the phone.
Okay, go ahead and draw what you see. We have a lot of light
Is it
now.
on D or E?
We are on D now.
Okay.
So this is location D from Earth. And as we look out from Earth, we see a lot of light and just a small shadow on the left. Something like that, maybe. And again, you can follow along in your flip book if you want. Did we gain light or lose light from C to D? Gain. So again, we're going to call this waxing. And you'll figure out here that from the new moon all the way to the full moon, we're gaining light, so the first half of the month is waxing. Now, this big shape of light, B-I-G backwards, is G-I-B, which reminds me that, oh, it's called a gibbous. It's called a waxing gibbous. So gibbous refers to this large area of illumination. Kind of like crescent referred to the small shape of illumination. Gibbous is big, and it's just a nice way to remember it. B-I-G backwards, gibbous. Big, gibbous, pretty easy, right? Okay. And again, this gibbous phase takes almost a week until we'll end up eventually at our last phase here, or not our last phase, our next phase here. Okay, what are you seeing? It's all light. It's all light. So you don't have to shade anything at E. Nothing shaded at E, and we're going to call it a full moon. That's our full moon. Yes.
I'll just write it on the back of my paper.
Now, as some of you were talking about on Thursday and Friday of last week when we were doing the moon phase stations, some of you were asking about eclipses. This is one of those locations where you might get an eclipse. And in fact, let me move the moon here and let me get my phone up off of the desk. Do you see that circular shadow back here?
Yeah.
Where my hand is now? See the circular shadow on my hand? That's the shadow of the Earth. So the sun shines on the Earth, and it actually does create shadows in space. If the moon moves into, here it comes, if the moon moves into that shadow, see how it goes from totally illuminated to dark? And then it comes back out of that shadow. That's an eclipse. Now, eclipses can happen here. They don't very frequently happen here because of what we'll talk about Thursday and Friday. But the basic idea is Earth is moving around the sun on a flat plane. So imagine the table we're looking at right now is the plane that Earth orbits. And we talked about this back when we talked about seasons too. We've got a flat plane, but the moon orbits on a slightly different plane. You read about it in one of your stations. It's something called inclination. The moon is not always in line and on the same plane as the Earth. Okay, the other issue we're having here is an issue of scale. I can only get these things so far apart in my room. The sun is not nearly big enough for our purposes, and the moon would really have to be very much further away. And so you're talking about a relatively small shadow in which the moon has to fit in anyway. So if it's just slightly above or slightly below that shadow, it's not going to be eclipsed. All right, and we'll talk more about that next week, or the end of this week, I'm sorry. Okay, so we got a full moon at location E. We're going to go ahead and revolve it a little bit more. Here it comes. My phone's going to be in the way temporarily. Here it comes. Watch for the shadow to come on. See the shadow starting to creep in? Okay. And there's your next phase. So this is now location F. Whoops. Location F. There's location F. Location F is going to look just like location D, but flipped. So we're going to have a small shadow on the right-hand side. And the rest will be light. So the light is going to start flipping to the opposite side because the moon has flipped over to the opposite side of the sun-Earth line. It's on the opposite side of that full moon now. So, did we gain light or lose light since our last phase? We lost some light. And the new name for this that you wrote down in your flip book last week was called waning. Waning. W-A-N-I-N-G. Please make sure you're spelling things right. And we already know the name of this big shape. It was the same as this big shape up here, it's just on a different side, is Gibbous. And again, please make sure you're spelling it right. And then the moon is going to keep revolving. There it goes. Watch the light grow.
I mean the shadow grow.
Well, yeah, that's true. So the light wanes, goes away, and we end up with kind of our 50-50 again. Yes, ma'am.
What would make that? That was like 50-50.
We're on G right now, yeah.
Yeah, but what
You'll
would
see.
make each?
Yes.
Okay.
Okay, so now we're at that halfway illumination. We are now seeing the light on the left, so I'm going to shade the right-hand side, just like you're seeing on the screen. And this is again one of our quarter phases. We lost light, so this is going to be our waning quarter. You could also call it the end of the third quarter, which is how we labeled it on your flip book. Waning quarter, third quarter. They mean the same thing. And again, the reason is, if we're going through a full cycle, we have gone through 1, 2, 3 quarters of that cycle. It's going to take us one more quarter of motion to get back to our new moon. Okay, and in the process, we're going to see a new phase. So watch the phase change as it moves. Here it goes. You ready? Losing light, losing light, losing light, losing light. We'll stop it there. And there's just a little sliver of light left on the left. So maybe something like this, and the rest is in shadow. And this should look exactly like phase B did. And it's going to have a similar name. We're losing light, so waning. And it's got the same shape, that tiny shape, called crescent. This is your waning crescent. And so the second half of the lunar cycle, the second half of the moon cycle, is all waning. So you start with waxing, more light, more light, more light. Then it starts to wane, it starts to go away for the second half. Until you get back to the original beginning point. You can watch it kind of go away, boom, and there's your new moon again. And this cycle will just repeat indefinitely, just keeps going over and over again. Now, here's something really important to think about. Some of you were asking me last week, can you see the moon during the daytime? Yes, you can. And in fact, if you think about it right now, look at the screen. It's daytime. The moon is up. I can see the sun, which means it's daytime, and there's a moon. So some of the moons, and now I'll move this so you can actually see it. Okay? Some of these moons, we'll go from above. Only the people in the daytime side of the earth can look out and see this moon. The folks that are having nighttime right now, they literally can't see it because it's on the opposite side. They're looking out over here into nothing. There's nothing over here. Now there might be other stars and planets they can see, but there's nothing, there's no moon for them to see. It's over here. Likewise, half a month later, a couple weeks later, during the full moon phase, people in the daytime can no longer see the moon. It's still daytime, so the sun's up, but there's no moon in the sky. Only at nighttime can you see the full moon. And then in other phases, for example, our third quarter, here's our third quarter phase. This is location G on your paper. This is happening kind of at sunset. I'm sorry, sunrise. So as people on the nighttime side are rotating into the daytime side, they're seeing this moon. So you can see this quarter moon sometimes at night, sometimes in the morning, but you'll never see it at sunset. Does that make sense? Likewise, the first quarter moon, you'll never see at sunrise. You'll only see it at sunset times. So maybe late afternoon, early morning hours, that kind of stuff. But you'll never see it in the early morning. Okay, does this make sense?
Indeed.
Hold on. Write it down.
I did.
All right. So let's get back to crescent phase. Next thing I want you to do, on your paper somewhere, I want you to write REV with a colon, ROT with a colon, and the word phase with a colon. Just somewhere on your paper.
Can it be on the back?
Do it on the front somewhere. There's plenty of white space there. So we said this process takes about a month, but let's put an actual number to it now. How long does this set of moon phases, how long does it take the Earth to revolve exactly once? So that would mean, how long would it take for the moon to start in that location, go around the Earth one time, and return to that location relative to the Earth? How long would that take, Dominic?
Then,
Do you remember?
no.
It's about a month. Brooke, do you remember the number?
Is it 29.5?
It is not. Jessica?
Okay,
It's the other one.
it's 27 point, it's either 3.5 or 9.
27.3 days. 27.3 days. Okay, and you might see some various decimals there, but 27.3 days is how long it takes the moon to go around the Earth exactly one time. How about the rotation? How long does it take the moon to rotate? First of all, does the moon rotate?
Yes.
Yeah, and you learned about that in the video, and we'll talk more about it here in a second. How long does it take the moon to rotate? Matthias.
27.3 days.
It's the same. 27.3 days. Now, because the moon is both rotating and revolving at the same rate, that's why you're only seeing one face of the moon. Did you notice I had a little X on the moon?
Okay.
Okay, the reason I did that is what you can do is you can take the moon, get a little lag on the camera, what you can do is you can take the moon and make that X face the Earth the whole time, and you'll notice that as I'm revolving it, I'm having to very slowly rotate the moon in my fingers to make that X always face the Earth. Look what happens if I don't do that. Look what happens if I just revolve it without rotating it. Uh-oh, the X is not facing that Earth anymore, which we know isn't true. We know that one face of the moon always faces the Earth. I'll show you that picture here in a moment. So in order for this to exactly match up and face the Earth at all times, it has to rotate and revolve at the exact same rate. Let me show you the picture here. With your own eyes, not in pictures, you've only ever seen the image on the left of the moon. So if you look out, whatever phase it's in, you've only ever seen this image on the left. You've never seen the one on the right. This is the far side of the moon, the one that faces away from Earth at all times. You've never seen it. Okay? This is a picture from like a satellite. Why does it look so different? Well, because it's got a lot of craters on it, first of all. It's got a lot less of these black patches, which are lava flows. Do you remember the lava flow that we learned about with the mice? The rock pocket mouse? The black desert lava flow? That's similar to this. So the moon, our best guess about what happened with the moon and how we got a moon is that as Earth was forming in its kind of baby state, not quite hardened yet, it was still very soft, a big meteor or a comet or something came, smacked into the Earth, ended up chunking a big piece off that reformed into a spherical shape is now our moon. So the moon is made of the exact same types of rocks that you find here on Earth. They are the exact same age as the rocks you find here on Earth. And for a long part of the moon's history, it was seismically active, which means there were earthquakes on it, well, I guess moonquakes on it. There were lava flows on it, and that's how lava flows that give it these dark, splotchy type areas. They would look really similar to what we saw in that desert with the rock pocket mountains.
So like, why isn't there water?
There's no atmosphere on the moon. So even if there was water at some point, it's not there anymore.
So,
There's nothing to keep it.
so basically the moon is just these extra.
It's just rock,
It's
that's
just
all,
from the earth.
from the Earth at
So
one
it's
point.
part of the earth.
It was part of the Earth.
Okay, so could the moon fit inside the earth?
Yeah, the moon is about a sixth, I think, the size.
So it's small.
So it's relatively small, yeah. My scale of the stress ball Earth and the moon golf ball is very off. It's a lot smaller than that. That's part of the problem that
I
I
thought it was a ping pong ball.
Is the lava flows the reason why when it's nighttime and stuff and you look at the moon, it looks like it has a face?
Yes, exactly. It's those dark patches. Christian?
Whoever went on the moon, I think it was Neil Armstrong, whatever, and some other people. Yeah, actually, the first people were Russian. But
No,
anyway.
we're not.
They
No,
were?
they weren't.
Oh, anyway, but, when they got there, did they, breathe?
No, there's no atmosphere.
Oh,
So they had to be in their extravehicular suits.
Did they take any, like, rock back?
They brought 400 pounds or something throughout the several missions that landed. Yeah. Avery?
How did they know that, like, that was like an asteroid colliding in there?
That is our best guess. Obviously, we don't know 100% certainty because it was so long ago, but based on the analysis of the types of rocks that you find on the moon compared to the Earth, we know they had to be the same at some point. Because it's the exact same minerals and everything we find.
Okay, so like, what's the moon's size of like diameter?
I don't know that number.
And then like, is it like an actual like perfect circle?
It's not perfect. No planet is perfect
Yeah.
spherical, but it's relatively spherical, yeah.
Um,
And it's got mountains and valleys just like Earth does.
It does.
Yesterday, we were in a car driving home from my aunt's, or my grandma's, and I laid my seat back and I could see the moon, and I think it's really cool that you can see it like that.
Yeah, absolutely, yeah. Christian?
Well, these craters, could they at one point been filled with water?
Probably not.
Where'd they come from?
Asteroids hitting the surface,
Oh, water.
creating just impact craters. Yeah.
Fun.
Some of those craters that you're seeing on the, especially on the right-hand side, some of those are hundreds of miles wide. I mean, they're massive.
How long, wait, if you were on the moon and you just started walking, could you fall off?
No, it's weird.
no, it's not flat.
There's still gravity, if that's what you're
Oh,
asking.
there's still
There's
gravity?
still gravity. Because the mass is a lot lower, the gravitational force is a lot, so have you ever seen the old footage of the astronauts? They kind of look like they're floating almost. It's not that they're floating, it's that the gravity's not pulling them down as quickly as it does.
So there is gravity, just not as much.
It's like, it's whatever the mass difference is, it's proportional to the gravitational
Very
force.
well.
So did like more asteroids hit like that side, didn't it?
A lot more hit on the back. One of the reasons we think is because obviously if the front face is always facing us, whatever Earth's gravity pulls in, that back side of the moon is going to get hit with them before the front side ever would. So there's a lot more craters on the back than the front.
How come Earth doesn't have all those craters?
We do have craters.
Yeah, but we don't have that.
Not that many. No, we also have an atmosphere that burns stuff up. So a lot of those craters might have been caused by something the size of a baseball. If a rock the size of a baseball tried to come into Earth's atmosphere, it burns up immediately. It would do no damage to us whatsoever. You might see it as a meteor.
Like how, so it doesn't burn the rocket suit because rocket suits are so fast and it's.
The rock is moving so fast, it
Yeah.
gets superheated and essentially will disintegrate the rock into teeny tiny bits and burn it up.
A rocket.
A rocket. What about it? As we
Is
believe
it
it's
going
connected-
so fast that it won't burn up?
It's made of materials that won't burn at those temperatures. So we make them of specific types of metal alloys that won't burn. like the rocks do. So when astronauts come back from being at the International Space Station or as rockets are leaving, they've got special heat shields on them that prevent them from burning.
Okay, so you know how you said there's like lava splotches or whatever. How did the lava get there?
It just like any rock. Like we have rock here on Earth that is heated from the core on the inside. The moon would have been active like that at one point. Now it has since cooled, so there's no lava flow on it anymore. But it would have had lava flow like we have on Earth, volcanic type of activity.
Okay, so like if I were to go on the moon, dig like.
It would be
really
solid
big hole,
rock,
It would just be rock.
just rock. Yeah, there's no active heat core.
So.
Whatever question comes up, write down because I gotta move on a little bit here.
Oh, my own. So how does the Earth have a shadow in space if it's like dark and stuff?
Well, because the light is being blocked by it. Just like anything that creates a shadow. You just don't see the shadow unless something goes into it.
Would we have to remember these names?
Yeah, you're gonna have to know these names. That's why we made the flip book, so you can flip through there and easily see the name with the phase. You're gonna have to be able to match up. If I said, hey, here's a picture of a phase, you should be able to tell me that as a waning gibbous just based on what you're seeing. And we'll practice enough that you should be pretty
You should
good.
make an image.
Possibly I could, yeah.
Oh, yeah, that's a good
All right.
idea.
Now, this whole revolution versus rotation thing, the reason that the same side, the same face of the moon is always directly facing Earth is because it's both rotating and revolving at the same rate. So that face gets locked in, basically the gravitational forces of the moon and the Earth acting on each other, pulls it and kind of keeps it stuck face to face with the Earth, so that you never see the backside of that moon. Okay, we'll talk more about that as we move on this week. But how long does it take for us on Earth to see the phases change? To see the phases change. So it takes 27.3 days for the moon to go around the Earth one time. How long does it take us on Earth to see the moon start at a new moon and get back to a new moon phase? How long? Luke?
29.5.
That's the one. Okay, make sure you label that on your paper. 29.5 days. Now, why the difference? Why the difference? Why would it be different? Why would it be different? Here's what I'm going to do. I'm going to turn this around. And I'm going to grab my Earth and my moon. Boop. Okay. Now, there's the sun. Actually, let's do it this way. You've been looking at it this way the whole time. Okay? Sun, moon, Earth. This is a new moon phase, right? They're directly in line. It's daytime, new moon. Sun, Earth, new moon. Sun, Earth, new moon. Correct? One trip around the Earth, we said, takes 27.3 days. How come it takes us longer to see the phases? Do you remember? Kind of mentioned in one of the videos. Okay, do you remember?
The Earth's revolution.
Earth's moving. The whole time we did this back on the desk, I just left the Earth there. That's not accurate. This takes 27 days. The Earth moves a lot in 27 days. It's going around the sun too. So as the moon goes around the Earth is going around the sun. Right? So here's the deal. Here's the important part to look at. Here's a new moon. I know it's a new moon because the moon is directly between the Earth and the sun. Notice the moon and the Earth are also in line with that wall over there. Okay? I'm going to go through a month of a revolution, 27.3 days. 27.3 days later, back in line with that wall. Beautiful. But it's not a new moon yet because, well, there's the sun and here's the Earth, and in order for it to be a new moon, those have to be in line. This is really, really similar to that solar and sidereal day thing. Remember that? Earth goes around the sun Earth rotates 23 hours and 56 minutes. But because it's revolving, it takes a little bit longer to get back relative to the sun. Do you remember this? This is the exact same principle. If this is a new moon is when the moon is between the Earth and the sun. if we revolve exactly one time, the moon is not between the Earth and the sun yet. It takes that extra 2 days or so to get back in line with the sun and the Earth. So that's why we have a longer phase time than we have an actual revolution.
Does the sun rotate?
It does.
It does.
It does, just not in a typical way that you might think that planets are rotating.
It rotates in place.
Does it go upside down?
It kind of rotates differently based on what part of the sun you're looking at.
What about the one that we can see?
So you'll have to look. You'll have to look it up.
Okay,
Another question.
so you guys, so how strong is the moon's gravity?
It's about. And I'd have to look the mass. It's up.
Okay.
It's like 1/5 or 1/6 as strong as the Earth. So not as strong as the Earth.
Okay, is it true that like the moon makes ocean waves?
The moon does not make waves. The moon generates tides, which we're going to talk about at the end of this week. The waves are generated from usually wind pushing on the surface and kicking it up. We'll talk about how it works later. Avery?
Okay, so like the moon rotates around the Earth and stuff. Well, what if our sun has only on the Earth is like their little moons, and the sun rotates around the bigger suns?
It does kind of work that way. So the sun is one star in the Milky Way galaxy, and all of the stars in the Milky Way galaxy are circling around the center of that galaxy, and at the center of our galaxy is a very supermassive black
So
hole.
how long does that rotation?
That rotation, I think we looked it up the other day, is like 280 million years or something for one rotation.
That was great.
So, yeah. I think that's what it said.
Rotation. Okay.
Maybe it was billion. I think it was billion.
Oh, that's nice.
You'll have to look. I don't remember.
I'll look at
Go ahead. No.
I'll make one.
First, is there like
Christian.
any other suns, like in different?
Anytime you see a star, it's a sun. Sun is just a star.
And then another thing is, does every planet have a moon?
No, they do not.
Because I know one.
Mercury does not.
Isn't Mars have like 7 moons?
I don't think Venus does. We have one. Jupiter's got like 74 or something.
Oh, I was.
Saturn's got like 80 or something. I mean, it's the crazy amounts of moons because those planets are so massive.
So like your moons, but
We're
our
not big
moon
enough to
doesn't
use
really
that
have
kind of
a
stuff.
name.
We don't have the stuff around us to have it.
Is it possible for anybody to go on one of Jupiter's moons?
Yes, if you could get there.
Well, are we able to get there now with our technology?
No, it takes too long. Well, we could get there. We could bring it back. And all the space agencies have a policy that if we send somebody out, we have to.
Okay, so what if it's like, so it would basically take them a lifetime?
That would make fun. So like there's like
Hey folks, we still got nice questions being asked. Please stop talking. Possibly the gas giants and the outer force are so big, it pulls more stuff from further away. We don't have that. We're close enough to the sun. It's the sun's gravity that actually take over that stuff. They're so far away from the sun. Their gravity is more important out there than it is.
So for the moon's like rotation, how fast? Like, if I was going up it right now.
Oh, it's still going.